Thank you, Gil. And good morning. My name is Katsuya Stoyama from NTT, and she is Chika Yoshimura from NTT Communications. And as you know, NTT Communications are providing the global internet services with Vario. And also in Japan, we are providing the internet services called OCN. And as a basic service and as a basic infrastructure, we provide the DNS cache servers for our customers. But these days, we have sometimes we have an experiences of a heavy load of those cache servers. So today, we would like to talk about our experiences of the heavy load of the cache server and result of the analysis and lessons learned. Okay? And as you know, the DNS world, there are several players. These players are categorized into the three. The application or operating system on the user devices and on the user side. And it is called a stop resolver sometimes. And secondly, the authoritative servers, including DNS servers and TLD servers, and as you know, the DNS cache servers provided by ISPs or the universities. And some kind of impact due to DNS anomalies are people are focusing on the DNS root servers. But as I mentioned, also the DNS cache servers sometimes suffers a kind of a burden of the heavy load. Okay? So the burden of the DNS cache servers sometimes caused by misconfigured DNS authoritative servers. The lame delegation is well known, but other factors exist as well. So today we would like to talk about our two experiences. One is caused by the virus and the worm activities, and the other is a large resource set and the TCP filtering. The first part is presented by me, and the second part will be presented by Chika-san. So let's go into the first part of the presentation. And in the United States and in the globally, the MyDoom was there was MyDoom, one of the virus in the world. Okay, the MyDoom attacks SEO website, and some species attacks Microsoft website. When MyDoom is activated, it's going to resolve this name of the website into an IP address. And we also have an entity in Japan which attacks XCCSJP, we call XJP, the website. The XJP is abbreviated from Association of Copyright for Computer Software, and this organization is watching the illegal copy of the computer software. And entity is a worm that is infected through a famous Japanese P2P software, Witty. And some species of entity attacks the XJP website on the first Monday of the month. And when they're trying to connect to a website, it resolved FQDN www.xjp.org.jp. So when the entity is activated, of course you know the DDoS attacks going through the ISP's network, and the target website is under attack. And access line is filled with the DDoS packets, and the backbone is also sometimes filled with the DDoS packets. And in this case, the owner of the website removes a record of the target website, okay, to avoid the attack from the affected users. And in April, when Anthony attacked, the owner of the website removed a record from authoritative server. At the time, the query sent to a DNS cache servers and returned the NX domain from the authoritative server. And the NX domain is also returned to the user, but there is no IP address, so the worms cannot attack the website. So the owner of the website can escape from the DDoS attack. But the query, because then they cannot get the IP address of the target website, they repeated the query to our cache servers. So, therefore, our DNS cache servers they suffered a heavy load. Okay, so why the DNS cache overloaded? A resource record removed from authoritative servers, and NX domain was returned, and its TTL was short in 60 seconds. And as I mentioned, worms repeatedly sent queries even if they could not resolve the name. The highest was approximately 700 queries per second from one IP address. This seems to us that negative cache negative cache are not effective in some operating system or applications. So someone make a negative cache disable at any time. I don't know exactly. So, but we have to fix it quickly because then our DNS cache servers were on a heavy load. Okay, so we prepared a fake zone and forward the queries to the zone to this server. Okay. So the query not going to an authoritative server, and this fake zone returned the black hole IP address. And also we prepare the routers which had the black hole in our network. So the packets destined to the black hole IP address are discarded at our routers. So the target of website can escape from the DDoS attack. And also, we can get our DNS cache servers reduce the load. And this worked very well in an April attack. So we decided to use this this method again in May. And these graphs show the total queries at our DNS cache servers. And the top graph is that April attack, and the bottom is an attack in May. And when DDoS began, and the owner of the website removes a record, the number of the queries are increased very dramatically. But then, when returning the black hole address, the number of the queries are reduced to the normal. Okay? And at the time, we captured the DNS packets and analyzed those packets precisely. And this was a graph of the May attack. And please be careful about the y-axis. Y-axis is a logarithm scale. So the spike of this, this spike indicates an extremely large number of queries. And during the day, May 3rd, we had a much more queries than usual. Okay? And we analyzed the correspondence between the answer of the DNS and the number of the queries to resolve the FQDN of the target web server. This graph shows when NX domain returned, the number of the queries to resolve the FQDN is dramatically increased. And after returning the black hole address, the number of the queries becomes normal, slightly normal. Okay? And I'll skip the slide. And in April and in May, we have succeeded to reduce the DNS cache servers. So we collaborate other ISPs in June to defend this attack. We prepared our own black hole address and encourage ISPs to use that black hole address, and also encourage ISPs to set the black hole of that outlet in their network. And we also asked the owner of the website to return the black hole address we prepared. So the queries to our cache servers and return the black hole address from the DNS authoritative servers, and were going to attack to the black hole address, but then those packets were discarded at the router of the participating ISPs. Okay, so the lessons learned from this attack is removing a resource record is not a good method. The combination of behavior of worms, stub resolvers, user, and authoritative servers will sometimes cause DNS cache server to collapse. And collaboration between victims and ISP is required. Okay? And if we have the generic black hole addresses and ISP set the generic black hole addresses to their routers, the owner of the authoritative server has only to return the generic black hole address to escape from the DDoS attack. So I think we think that some kind of a generic black hole address is necessary. Okay. So this is the first part of the presentation. So next we're going to second part. So let's listen, please.
Good morning, everyone. I'm Chika Yoshimura, working at NTT Communications Corporation in Japan, and we operate OCN, an ISP in Japan. In June, we found that there might have been inadequate setup of an authoritative DNS server, which made our cache DNS server overloaded. In order to alleviate the overload on our server, we took a couple of approaches. In this presentation, I'm going to briefly explain what the problem was, what caused the problem, and how we solved the problem. Here, when we say overloaded, we mean high CPU utilization caused by a named daemon. Recently, one of our cache DNS servers suddenly became terribly overloaded. We found that our server tried to establish TCP sessions with an authoritative DNS server, which failed three-way handshake at the sent state. Why did our server try to establish TCP sessions with the authoritative server? As you know, DNS servers try to communicate with other DNS servers by UDP, except in special cases. At that point, we didn't know why our server came up against this situation. Usually, the number of TCP sessions is around 5 in our cache server, but in this case, we found around 120 outstanding connection attempts. The number is too large compared to the usual. From investigation, we concluded that the packets with TC bit caused the increase of TCP sessions. As you can see in these graphs, they seem to synchronize with each other. As you know, TC or truncated bit is set in responses when entire set of resource records can't be accommodated in one UDP packet. Now, what happened to our server? Let's look at the next slide. End users directed queries to our cache server. Then the server performed recursion and finally asked the authoritative server. This action is described with arrow 1. But in this situation, because the answers from the authoritative server didn't fit in the 512 octets payload size limit, the entire answer couldn't be accommodated in one UDP packet. The server returned a packet with TC bit and required our cache server to ask again using TCP. This action is described with arrow 2. Consequently, our cache server queried the authoritative server to get the answer with TCP packets. However, the authoritative server seemed to reject the TCP queries. These actions are indicated by arrow 3. Although the cache server tried to retransmit queries by TCP, our server could not get any answers from the authoritative server. The cache server waited for about 75 seconds and ended up with timeout. If there were 5 authoritative servers of one domain, a cache server repeated the same operation 5 times. If one of authoritative server is able to accept TCP queries, our server can get the answer from the authoritative server. The reason for increase in failed TCP sessions was that our server kept retransmitting queries by TCP despite of the fact that these accesses were rejected by other side. While our server waited for the responses, it kept retransmitting TCP queries. As a result, our server was overloaded. An example of contents on packets is shown in the next slide, but I will skip the detailed explanation and go on to talk about our workaround. After the trouble, we took some actions to attenuate the impact of TCP sessions. Although we emailed several times the administrator of the domain to accept TCP connections or reduce their name records to fit in 512 octets, they still have not answered our request until today. While we waited for their action, our server was gradually getting overloaded and battery affecting all our internet users using our cache server. To avoid this situation to become worse, we used the option black hole on the cache server in order to reject the queries from the users that caused our cache server to be overloaded. If our goal is just to keep the server low load level, there is another possible approach. We could modify bind's code on our server so that it won't send a query back when truncation occurs. Meanwhile, it would send the server fail response back to end users. Both This approach and the action we took, which was to black hole users' queries, are effective to alleviate the overload on a cache server. However, these approaches do not allow a cache server to serve its own purposes. A cache server should respond to queries with right information. An authoritative server is expected to configure as suggested in RFC. In order to avoid future occurrences of the same problem, we suggest that every DNS administrators review their DNS server's configuration. Regarding this problem, there seem to be the three reviewing points we think. 1. Open TCP port 53 for TCP queries. RFC 1123 recommends answering TCP queries. It's not possible to open TCP port 53 because of some special reasons. We strongly recommend that RST reset packets should be returned. And 2, when possible, set the size of answer to be smaller than 512 octets. Or 3, support eDNS 0 on your DNS server. If you support this, we can get answer over 512 octets from the authoritative DNS server without TCP connections. Thank you.
So the wrap up. Through our experiences, please be friendly to DNS cache servers. So, administrators, please check and modify your settings of the authoritative servers. And instead of using removing a resource record in case of DDoS, please use some black hole address. And from the second experiences, please configuration should be consistent. Yeah, oversized resource sets, no EDSL and cross TCP port is not good, but we can often see this setting. Okay, thank you very much.
We have time for a few questions. I'm going to ask Philip. Philip?
Right here.
Philip has, oh, there you go. I thought you had left the building. Are you prepared? Okay, we will take a few questions.
My name is Spencer Dawkins. I had a question about the TCP filtering with the large RR set. That query would have failed for anyone trying to. I guess what I'm asking is, you were talking to an admin who wouldn't reduce the size of the RR set, but was that query working for anyone?
Oh yeah, we've asked the administrator to reduce or open the TCP port, and it may affect all of the users. I think the answer is
Oh, you just did.
Oh yeah, okay, so hopefully.
It's just like black holing was the right thing to do.
Yeah.
Hi, I'm Sam Weiler. Maybe Rob Thomas is in the room because you may want to get up and answer this. For your proposal that you use a well-known black hole address, I'm wondering what happens if you play that out a few more steps. Do the miscreants change their code to detect your black hole address and just have their code fall over and die? Mm-hmm. Do they quit using the DNS entirely? Mm-hmm. Where does that play out?
Oh, you mean that using a generic black hole address cause another attack for you mean?
When you use a well-known address, the attacker will know that also.
Attack another site?
Yeah,
okay. I'm very sorry.
Hi, Bill.
Hi. This is me speaking Japanese, or not, as the case may be. Yeah, using well-known addresses is a bad idea. Don't do it if you can get away with it. If you can't get away with it, you're in trouble. Having honeypots and other such things to catch people is, it's part of the arsenal of things that you have. So if you have a quote-unquote well-known black hole address, and people find it, you're going to have to move it eventually, because people will find it out. But this is a technique, one technique that has been demonstrated to work in today's environment. Will it work 5 years from now? Probably not, or at least it won't be as effective. But there are, the IAB and the IETF people have come out and said use of well-known addresses is probably a bad idea. So this one works now.
Thank you.
More questions? Okay, thank you very much.
Thank you very much.